Model building. How do we decide which variables to include in a multiple regression model? When building a multiple regression model, we often have many candidate predictors: age, sex, smoking status, BMI, exercise, and more. But we can't just throw them all in. Including too few variables means we miss important factors and confounders. Including too many can lead to overfitting, where the model captures noise rather than real patterns. We need a principled approach to model building. A key tool for model building is the adjusted R-squared. Ordinary R-squared measures the proportion of variance explained, but it has a fatal flaw. It always increases when you add more variables, even useless ones. Adjusted R-squared fixes this by penalizing for each additional variable. It divides by the degrees of freedom, so adding a worthless predictor actually makes it decrease. On this plot, R-squared keeps climbing with more predictors. But adjusted R-squared peaks at 3 predictors, then declines. This tells us 3 predictors is the optimal model. One major pitfall in multiple regression is multicollinearity. This happens when 2 or more predictors are highly correlated with each other. Think of it as overlapping information. If X1 and X2 share a lot of variance, the model struggles to separate their individual effects. The consequences are severe. Coefficients become unstable with large standard errors. It's hard to tell which variable is really driving the effect, and coefficients may even flip sign. We detect multicollinearity using the variance inflation factor, or VIF. A VIF greater than 10 signals a serious problem. There are 2 main automated strategies for selecting variables. Forward selection starts with an empty model and adds the most statistically significant variable at each step. We keep adding until no more variables significantly improve the model. For example, we might start with nothing, then add age, then smoke, then BMI. Backward elimination does the opposite. Start with all candidate variables and remove the least significant one at each step. We drop income, then diet, until all remaining variables are significant. Once we have a model, we test each coefficient individually. For each variable j, we test whether beta j equals 0. The t-statistic divides the coefficient by its standard error, with n-k-1 degrees of freedom. Here's the output for the FEV example. The smoke coefficient has t equals -2.588 with p equals 0.01. The age coefficient has t equals 28.68 with a p-value below 0.001. Both are statistically significant, confirming they belong in the model. To summarize model building, always use adjusted R-squared, not plain R-squared, to compare models. Check for multicollinearity with VIF. Use forward selection or backward elimination to find the best set of predictors. And test each coefficient individually to confirm it contributes significantly to the model.